the what? Of the neutral axis. Okay. So we're going to calculate the stresses, and we're going to look at the location. And I'll go further is we are also going to find we're going to also sketch the stress profile. Okay. So from here, we realize that the structure will deform in which way. Okay. So you somehow, for now, okay, you're going to sketch how the structure will deform. So because of how the load is acting, right, our structure will deform this way. So this is our deformation pattern. Okay, so this is a sketch of the deformation pattern. So we know if the deformation go that way, over here, this is the center of curvature. Now the center of curvature, if you don't want to determine it, it's up to you. It's not really important, but I just want to highlight where the center of curvature is. And we know that the moment is acting this way. Right? How is bend? The moment is acting that way. And from here, you can analyze that at the head of the arrow, of the moment arrow, this will be under compression, and the top will be under tensile or tension. Let's call it tensile. So from here, based on your analysis, you are very, very sure that point A, right, that stress at point A is going to be in tensile mode. Okay, so stress X at point A is going to be in tensile, and stress X at point D is going to be in compression. B, don't know yet. Why don't know yet? It all depends on the location of the centroid. It can be equal to 0, it can be tensile, and it can be compression. So I don't know. We don't know yet. Okay. So anything else? Okay. So that is what we have gathered. Okay. So have all this information ready already. When you're analyzing your structure, these are the things that will help you. Okay. Then what we have, we're going to draw transformation. So on this transformation, based on based on the clamp, this is my X, my Y, and then this is the rotation on the Z. Okay, and then if we were to base on the cross section, this will be my Y, and this will be my my Z, and over here this is the rotation of the X. So it's important that you get the transformation nailed out already. Okay, so as you can see over here, what we have now is we know that our structure is classified as eccentric, okay, symmetrical, loading. So we are aware that the formula we're going to use is stress X will be equal to P in the X direction divided by A, right, minus by, so the moment, right, you can see the rotation of the moment. So this is the rotation of the moment. The rotation of the moment is about Z axis. So it's mz over izz multiplied by y. Okay. So why we classify as symmetrical loading? So if I were to put a point down here, so this point is my alpha point, and this point is my beta point. Okay. So what we realize later on when we calculate, we realize that stress X at point A is equal to stress X at point alpha, and stress X at point B is equal to stress X at point beta. So for this case, it satisfies the condition of symmetrical loading or symmetrical bending. 。 Okay, I'm going to call this symmetrical bending. Okay. So first thing of all, we are going to firstly geometrically identify the position of the centroid. And for this case, where we say that it's eccentric loading, we also know the fact that the centroid, the position of the centroid, okay, the position of the centroid is not the same. Okay, it's not the same as the position of the neutral axis. We are aware of that. Okay. Right. So I'm going to copy this image. Right, I'm going to paste. More important is I need this diagram over here. Right. So now I will advise you, because I've solved a lot of problems, right? I'll advise you for this problem over here, you should take the datum at the top. Okay, so the datum, so the symbol for datum is you're going to take the datum from the top. Okay, you're going to take the datum here, right? Why the datum has to be taken there? Okay, I will show you later why. Okay, but for now, my advice is to take the datum. If this is your neutral axis, I don't know where the centroid is. If this is the centroid, take the datum in the same site where the load is applied. Okay, so take the datum at the same site as the applied force from the centroid. Okay, I don't want you all to take your datum down here. Okay, so what I don't want you to do is I will not advise you to do this. Okay, and I'll show you why later on. Okay, I don't want you all to do this. I much prefer you to do this, right? And this is to help you prevent from making mistake later on, right? So we're going to take the datum from the top, and this is where my y will be moving, right? So if I were to draw our transformation over here, this will be my y, and that's my z, and we were interested to find izz. So we are interested to find zz in like this axis, and like what I told you before, anything that's parallel to the axis of interest, for this case izz, this is my width. Anything that's perpendicular, that is going to be your depth. So we're going to divide this into two now. So we have this as section 1 and section 2, and over here is where we're going to take all our reference from, our datum. Okay, that's where we're going to take our datum from. So we have section 1 and 2, and then we have our, so take your width first and depth, like what I think I showed you guys this last week, right? So the width is equal to 10, the depth is equal to 4, and for section number 2 is, so 20 minus 16. So sorry, for the other one, the width is 4, the depth is 16, so this will come out to be 40. 16 times 4 is equal to 64. Then we come out with the individual neutral axis, okay, small y bar. the individual neutral axis. So this is 4 divided by 2. The next one is 4 plus by 16 divided by 2. So this is equal to 12. Okay, again, the datum is taken from the top. And finally, we have omega, or width, depth multiplied by y bar. So 40 times 2 is 80. And then we have 64 times 12 is equal to 768. Then you do the sum. So summation. So this is 104. And this is 768 plus by 80, 848. So from here, we can calculate our centroid. Okay, so I'll call this centroid. From the top, which is our y bar, is equal to 848 divided by 104. So 848. So it's equal to 8.153 or 8.154 millimeters. Okay, so as I mentioned before, this is the position of the centroid, not equal to the position of the neutral axis, for the fact, okay, that we are under what? Eccentric loading. Okay, so now we're going to find IZZ1 and IZZ2. So like how I taught you guys before, you don't need to see anything. The analysis is in this box over here, right? So IZZ, I'll write up the formula in case some of you forget. So IZZ is equal to BD cubed over 12 plus by area multiplied by the global centroid minus by individual section centroid squared. Okay, so IZZ will be equal to 10 4 cubed over 12 plus by area of 40. As I say, I'm not thinking now. Okay, so 8.154 minus by 2 squared. Okay, I just follow the sequence that I taught you guys last week. So this is equal to 1568.21 millimeters to power 4. So this is also equal to 1568.21 times 10 to power minus 12 meter to power 4. So this is IZZ1. I do apologize, IZZ1. Then we proceed with IZZ2. So likewise, you have 4, 16 cubed divided by 12 plus by 64 multiplied by 8.154 minus by 12 squared. Okay, so you have 2312 times, or millimeter to power 4. So this will be equal to 23 12 times 10 to power minus 12 meter to power 4. Okay, so from here we have already compute our IZZ. So our IZZ will be equal to 3.8802 times 10 to power minus 9 meter to power 4. Now, I did forget to mention this. So we know that our centroid is 8.154, right? So looking at point B now, okay? Look at point B now. We know that stress X at point B, right, will also be in the what? Will also be in the tensile mode. Because the neutral axis, if I'm going to sketch roughly, the neutral axis or the centroid is going to be here. So this is the position of the centroid. Okay, so there's a position of the centroid. Right. So next, so we have our IZZ already. Okay, so now we can plug everything into the formula. So let's look at the formula first. Okay, so the formula states that stress X is equal to Px over A, right, plus by Mz over Izz multiplied by Y.